Hello and welcome to 5 Minutes of Postgres. My name is Lucas and today we're going to talk about a Postgres performance puzzle, Linux readahead, and tuning effective I/O concurrency. This blog post by Jeremy Schneider was posted a couple of weeks ago and it was posing a puzzle for the reader to solve. I'll admit I was lazy at the time and I didn't actually solve the puzzle, but Jeremy got a few interesting responses and we'll take a look today at the puzzle itself and then also at the solutions. In this puzzle, he was counting records in a table and he was limiting it by filtering on a certain column. There are two columns here that are relevant. The first query with the first column, that one took 500 milliseconds. The second query took over 100 seconds. That 600 times difference, that's pretty substantial and surprising. The question is, can you guess what the data in the table is? And we'll skip ahead a little bit here. The solution to this puzzle, the first column was just counting up like 1, 2, 3 as it was inserting data, versus the second column was random data. And this was distributed all across the index. You may also see behaviors like this, by the way, if you're using random UUIDs. We talked about this previously, but random UUIDs are very ineffective in terms of index composition. In this follow-up blog post, he goes through how to debug this problem, because oftentimes it may not be as obvious, and having good tools is important. He starts with explain analyze, and he does two things here that I think are worth noting. First of all, he specifies the buffers option to explain. That's always a good idea to specify when you run explain analyze. Second thing he does, and this is something I don't actually do as often myself, he enables log executor stats. That runs an operating system function called getRUsage to collect extra metrics during the execution of the query. This will tell you what happened in the operating system level process, like how much data was read on a file system. What's odd about this first query is that if you divide the I/O time by the number of blocks that were being read, the average latency of a read request, it's very low. Each page that was being read was very fast. The second query takes over 100 seconds and it reads a lot of blocks. If you're reading a lot of data, that's going to be slow no matter what. We know that this index layout is ineffective. Let's just look at a smaller portion of the index. When you look at the numbers, you'll find that the individual I/O, so the individual page that's being loaded, takes about 0.4 milliseconds. Underneath the hood, this is using GP2 EBS volumes. This is network request, so 0.4 milliseconds, that's actually reasonable. You can do some more analysis, but what's interesting to understand is that Linux readahead is the reason that the first query is much faster. The way that somebody who works on this on Linux kernel describes it is readahead takes a risk, reads more than is needed, and then if that brings a reward, as in somebody actually requests that data later, then it reads even more ahead because it thinks that you're reading sequentially. Instead of you having to wait on each page, it reads ahead and it fetches that data into the OS page cache for you to read from the cache instead. Jeremy does a little bit more analysis here in terms of readahead. The main point that I would make is that readahead helps you improve performance, especially on the network EBS volume. Linux readahead is only effective when you have sequential data. There are cases where Postgres can help Linux. If you have a Bitmap heap scan, so it looks at the table data, Postgres actually has the index itself that will tell it where in the table it's looking for data. Effective I/O concurrency in Postgres tunes how much Postgres is telling the Linux kernel to look ahead. When you set effective I/O concurrency to a value, let's say 10, that will say instead of getting one page from the main table at a time, will read ahead multiple pages by telling the Linux kernel, hey, I'm going to need these other pages soon. This is very useful. If you have a system that has high concurrency supported on the drive, for example, EBS volume, the default value here is not going to be good enough. Surprisingly, Amazon RDS doesn't set a useful default value, in my opinion. They don't change the default, and default is 1, which means a single request is going to be requested ahead, which doesn't really help you. Somebody actually did a benchmark of this a couple of years ago where they were comparing two cases. A sparse bitmap scan, which effectively means it's looking at a lot of different locations in the table, and a dense bitmap scan where they were looking at very closely related data that's right next to each other in the table. If you have a sparse bitmap scan, what you want is a high effective I/O concurrency. You want something like 32, 128, or even 512. Depending on how many active queries you're running, maybe 32 makes more sense, but certainly the default of 1 doesn't make sense. On the other hand, if you have a very dense bitmap heap scan, so if you're looking at very closely related data, turn effective IO concurrency to 0, because then you defer back to the Linux readahead behavior to default, which will assume sequential scans ahead instead of trying to override that behavior with Postgres. Thank you so much for listening. This was 5 Minutes of Postgres. Subscribe to our YouTube channel to hear about next week's episode, and talk to you next week.